We'll start in 1 minute. Today and tomorrow we'll review for test 2. Test 2 is on Friday, and it's over section 7.7, 7.8, 8.1, 8.2, 8.3, 9.3, and 9.5. And we'll start with an example using function values on regular intervals to approximate a definite integral of that function. So we will approximate this integral by using Simpson's rule and the trapezoidal rule. So as a reminder, the formula for the trapezoidal rule, if you have n intervals, then the approximation of the integral is delta x over 2 times this quantity, f of x of 0 plus 2 times f of x of 1. All of the intermediate coefficients are 2. Okay, that's the trapezoidal rule. This is to use to approximate a definite integral of a function of x. Simpson's rule. Remember, when you're using Simpson's rule, the number of intervals is even, so the number n is even. So Simpson's rule is delta x over 3 times the quantity f of x of 0 plus 4 times f of x of 1 plus 2 times f of x of 2. The coefficients alternate 4, 2, 4, 2 throughout the intermediate parts. And at the other end, we have 2 times f of x of n minus 2 plus 4 times f of x of n minus 1 plus the last term, f of x of n. You can read my writing, but you no doubt have that memorized already anyway. Okay, so in our example, the value of delta x is 2. The length of each subinterval is 2. And there are 6 subintervals. So t sub 6, delta x is 2, so 2 over 2. And the first function value is 11.6. And then plus 2 times the next function value, which is also 11.6. And then plus 2 times 11.1 plus 2 times 11.7 plus 2 times 12.2 plus 2 times 12.6, and then the last function value is 13. So for now, this is good enough for our purposes. So even on a test, this would be a satisfactory answer. Just focus on getting the coefficients correct. Using Simpson's rule, the approximation is 2 over 3, that's delta x over 3, and then 11.6 plus 4 times 11.6 plus 2 times 11.1 plus 4 times 11.7 plus 2 times 12.2 plus 4 times 12.6, and then plus 13. In general, Simpson's rule is a better approximation. Okay, moving on to part 2. Do the integrals converge or diverge? And if they converge, evaluate those, determine what they converge to. Okay, so this one we have an improper integral from 1 to infinity. The integrand is 1 over 2x plus 3 to the third. So if it helps, you can use a substitution. You substitute u to be 2x plus 3. And so du is 2 dx. And so 1/2 times du is what dx is. And then we can rewrite this improper integral. We have a factor of 1/2 out front. And the integrand is 1 over u to the third du. And the lower limit, well, when x is 1, the u value is 2 times 1 plus 3, or 5. And when x approaches infinity, so does u. U also approaches infinity. Okay, we know that this one converges. We know that it converges because the exponent on u in the denominator is greater than 1. So we know that it converges. So we'll find what it converges to. You can write this as 1/2 times the limit as b approaches infinity of the definite integral from 5 to b, and then replace 1 over u to the third with u to the negative 3. So we get 1/2 times the limit as b approaches infinity. The antiderivative is u to the -3 plus 1 divided by -3 plus 1. So that becomes -1/2u to the second. And then from 5 to b. So evaluate this when u is b, so we get -1/2b to the second, and then minus -1/2 times 5 to the second. And when we compute this limit, 1/2b to the second goes to 0 as b goes to infinity. And so we have 0 minus -1/2 times 5 to the second, which is positive 1/50. So the limit is 1/100. Okay, the next one, the improper integral of 1/the cubed root of x to the second as x ranges from 1 to infinity. Well, let's rewrite this. Let's convert the cubed root of x to the second to exponential form. So the cubed root of x to the second is x to the 2/3. So we automatically can say that this improper integral diverges. And in the denominator, the exponent 2/3 is less than 1. So that's how we know that it's going to diverge. Okay, the next example is also an improper integral. Even though the interval from -3 to 6 is a finite interval, the integrand, 1/the square root of x plus 3, is not defined when x is -3. So we'll see if we can determine what the value of this is. Let's let b approach the number -3 from above or from the right. And the definite integral will be from b to 6. And I'm going to replace 1/the square root of x plus 3 with x plus 3 to the -1/2. Okay, an antiderivative of x plus 3 to the -1/2 is x plus 3 to the 1/2 divided by 1/2, or 2 times the square root of x plus 3. Okay, then we evaluate the integral. So when x is 6, we get 2 times the square root of 9, and then minus 2 times the square root of b plus 3. Well, as b approaches -3 from above, b plus 3 approaches 0. And then, so the limit is 2 times the square root of 9, 2 times 3, or 6. Okay, on the next page, determine the arc lengths of the curves over the specified intervals. Okay, so in the arc length formula, I'll write that down here, the arc length of a function y equals f of x on an interval from a to b is the definite integral from a to b of the square root of 1 plus the square of the derivative dx. Okay, so our function, it's not called f of x, but you could write f of x equals x to the 3/2. Anyway, we need to find the derivative. The derivative of y with respect to x is 3/2 times x to the 1/2. And so the arc length on the interval from 0 to 4 of the square root of 1 plus the square of the derivative. So when we square 3/2 x to the 1/2, we get 9/4 x. And we can go ahead and evaluate this. If you use a substitution, if you assign u to be 1 plus 9/4 x, then du is 9/4 dx. And so we'll replace dx with 4/9 du. Okay, the constant factor 4/9, we can bring that out front. So this is 4/9, and then times the integral of u to the 1/2 du. And then we have to find the limits of integration. So the lower u value occurs when x is 0. When x is 0, u is 1. And the upper limit for u, when x is 4, the u value is 1 plus 9/4 times 4, or 10. Okay, then we have 4/9, and then an antiderivative of u to the 1/2 is 2/3 times u to the 3/2, evaluated from 1 to 10. So we can multiply 4/9 times 2/3 to get 8/27. And then 10 to the 3/2 minus 1 to the 3/2. So that's good enough for the arc length. Okay, the next example, find the arc length of y equals x squared over 8 minus the natural log of x on the interval from 1 to e. Okay, we need to find the derivative, dy dx. We're going to get 2x over 8, or x fourth, minus 1 over x. So maybe if we have a common denominator, which is 4x, so combining this with a common denominator, we'll get x squared minus 4 over 4x. Okay, so the arc length, this will be the interval from 1 to e, and the square root of 1 plus the derivative squared. So we're going to square x squared minus 4 over 4x. Okay, we'll simplify what's inside the square root. So when we square this rational expression, the denominator is going to become 16x to the second. So in anticipation of that, I'm going to replace 1 with 16x to the second over 16x to the second. And the denominator of this term will also be 16x to the second when we square it. And the numerator, we're going to square x squared minus 4. And we'll get x to the fourth minus 8x to the second plus 16. Okay, so inside the square root, the common denominator 16x to the second. And the numerator, when we combine like terms, we'll get x to the fourth plus 8x to the second plus 16. Okay, now what? Maybe I should let you interject for a few seconds. Is anything nice going to happen? Yeah. Inside the square root, the numerator is a perfect square. This is x squared, the quantity x squared plus 4 squared. And the denominator is a perfect square. So when we take the square root of a perfect square, well, the square root of x to the fourth plus 8x squared plus 16, the square root of that is just x squared plus 4, right? And the square root of 16x to the second is 4x. Are we all okay with that? Okay, then we can simplify the integrand a little bit. Since the denominator has a single term in it, x squared divided by 4x is just x over 4. And 4 over 4x is 1 over x. And finally, we can find an antiderivative. An antiderivative of x over 4 is x squared over 8. And antiderivative of 1 over x is the natural log of x. And we evaluate this from 1 to e. So when x is e, we get e to the second over 8 plus the natural log of e is 1. And then we subtract 1 to the second over 8, or 1/8. And we subtract the natural log of 1, but the natural log of 1 is just 0. So this is just, we can write this as e to the second. 1 minus 1/8 is 7/8. So we can write this as e to the second minus 7 all over 8 for the arc length. Okay, the next example, find the arc length of y equals the definite integral from t equals 1/3 to x of the square root of 1 over t squared minus 1. On the interval, the x interval is from 1 over e to 1. Okay, so applying the fundamental theorem of calculus part 1, when we take the derivative of y with respect to x, we just take the integrand of the integral and replace t with x. So the derivative is the square root of 1 over x squared minus 1. Okay, so the arc length, this will be the definite integral from 1 over e to 1. And the square root will be 1 plus the square of the derivative. Since the derivative is the square root of 1 over x squared minus 1, when we square it, we're just going to get, and inside the square root, the 1 plus 1 over x squared minus 1 simplifies to 1 over x squared. And the square root of 1 over x squared is 1 over x. And then an antiderivative is the natural log of x, evaluated from 1 over e to 1. Okay, so what do you get when you evaluate that? The natural log of x evaluated from 1 over e to 1.
The final answer.
There's what?
Did you want the final answer?
Yeah, what's your answer?
I got 1.
You got 1? That's what I got. I got 1. So if we do it step by step, when x is 1, we have the natural log of 1, and then minus the natural log of 1 over e. The natural log of 1 is 0. 1 over e is 1 over e to the first, or e to the negative 1. So we're subtracting negative 1 times the natural log of e. But the natural log of e is 1. So the negative of negative 1 is 1. So that's the arc length, 1 unit. Okay, on the next one, number 4, find the surface area by revolving the curve about the indicated axis. So y equals the square root of 5 minus x on the interval from x equals 3 to x equals 5. Rotate that about the x-axis and find the surface area. Okay, so if we rotate a function of x about the x-axis, the formula for surface area is the integral over the interval from a to b of 2 pi times f of x times the square root of 1 plus the square of the derivative. Okay, so our f of x is, instead of f of x, we're writing it as y equals the square root of 5 minus x. So I didn't leave a lot of room, but so we need to find the derivative. So this is like 5 minus x to the 1/2. So it's going to be negative 1 over 2 times the square root of 5 minus x. Okay, so the surface area, the integral from 3 to 5, 2 pi times the square root of 5 minus x times the square root of 1 plus the square of the derivative. Okay, so when we square this derivative, the numerator will be 1 and the denominator will be 4 times 5 minus x. So we'll do some arithmetic. So the common denominator is, inside the square root, is 4 times the quantity 5 minus x. So 4 times 5 minus x is 20 minus 4x, and then plus 1, and then over 4 times the quantity 5 minus x dx. Hey, you can probably see what's going to happen. We have the square root of 5 minus x, and we also have in the denominator the square root of 5 minus x. So the square root of 5 minus x from the numerator is going to cancel with the square root of 5 minus x from the denominator. You see that? And in the denominator, we have the square root of 4. So when that comes out, it's like having 1/2. And 1/2 times 2 pi is pi. You see that? So if we write down what we have left after those cancellations, the definite integral of pi times the square root of 21 minus 4x. Okay, so to find the integral, well, if you think of u substitution, if u is 21 minus 4x, then du is negative 4 dx. So negative 1/4 du is dx. So we need a factor of negative 1/4 out front. And then think of the square root of 21 minus 4x as 21 minus 4x to the 1/2. So when we integrate, we'll get 21 minus 4x to the 3/2 divided by 3/2, which is equivalent to multiplying by 2/3. And we still have a factor of pi. And then the quantity 21 minus 4x to the 3/2. We'll evaluate this between x equals 3 and 5. So negative 1/4 times 2/3 times pi is negative pi over 6. So negative pi over 6. When x is 5, we have 21 minus 4 times 5, or 21 minus 20, which is 1, 1 to the 3/2, which is 1. And from that, we're going to subtract 21 minus 4 times 3, which is 9. And 9 to the 3/2 is 27. So we get 1 minus 27. And then negative pi over 6 times negative 26 is positive 26 pi over 6. And then in lowest terms, this is 13 pi over 3 square units, since it's the surface area. Okay, are we all in agreement on that one? Okay, the next one, this time we're rotating y equals a function of x about the y-axis. So what's the formula for the surface area this time? The integral from a to b of 2 pi. Instead of writing the function of x, we write the variable x times the square root of 1 plus the square of the denominator. Sorry, the square of the derivative. Okay, so we need to know the derivative, dy dx. 1/3 times 3/2 is 1/2 times x to the 1/2. Okay, so the surface area, the integral from 0 to 12 of 2 pi x times the square root of 1 plus the square of the denominator. I keep saying the wrong word. The square of the derivative. When we square the derivative, we get 1/4 times x, or x over 4. So if we have a common denominator of 4 and it's inside the square root, the square root of 4 in the denominator is 1/2. 1/2 times 2 is 1. So this can be written as the integral from 0 to 12 of pi times x times the square root of 4 plus x dx. I forgot the dx over here. Okay, how should we compute the antiderivative of this? Well, we can integrate by parts. So most of this I'll leave the rest of it for you to do. I'll just mention integrate by parts. So you can let u be equal to x. So du is dx. And dv is 4 plus x to the 1/2 dx. And so v turns out to be 2/3 times 4 plus x to the 3/2. And then after that, it's not too bad integrating that by parts. Okay, let's move on to the next sheet. So problem number 5. Suppose a vertically oriented isosceles trapezoid is in water. The top is 10 feet long at the water level. The height of the trapezoid is 15 feet, and the bottom is 30 feet long. So find the hydrostatic force on one side of the trapezoid. Okay, so we have the water surface. And the top of the trapezoid is at the water level. It's an isosceles trapezoid. So the top is 10 feet. The bottom is 30 feet. And the vertical distance is 15 feet. Okay, so if we assign x equals 0 to be at the water level, and then if the positive x values are downward, we're going from 0 to 15 downward. Okay, so we subdivide the interval from 0 to 15 into n subintervals, and corresponding to each subinterval is a rectangle. And we're going to use the rectangle to approximate the area of that part of the trapezoid. So at that level, we'll have a depth of x of I star, say. The vertical side of that rectangle is delta x. And we need to find the length of the horizontal side of that rectangle. So here we're using the hydrostatic force formula. It's the area of the rectangle times the depth, and then times rho times g. So normally we write rho times g times the the volume, area times depth. Okay, so in our picture, the depth is x sub I, and the area is the area of that rectangle. So we know that the length of one side is delta x, and we have to have an expression for the horizontal side. Okay, so if we look at that over here, so if this top side is 10 feet, and the entire bottom side is 30 feet, and it's an isosceles triangle, then we can reconstruct the trapezoid this way. So at a particular depth of x sub I star, we know that this part is 10 feet. We need to know the length of this and the length of that. These are the same because it's an isosceles trapezoid. So we can use similar triangles to help us determine what the value of A is. So we need to know A because the horizontal length of this rectangle over here is 10 plus 2 times A. So we know that it's at a depth of x sub I star. Okay, so let's just focus on this triangle on the right. This length right here is x sub I star. So x sub I star divided by A is equal to 15 divided by 10. So we solve for A. Let's just do the reciprocal. I could have done this to start with. A over x sub I star is 10 over 15, or 2 over 3. And so the value of A is 2 times x sub I star divided by 3. Okay, but we need 2 of those. So this side, the horizontal side of the rectangle, is 10 plus 2 times A, or 10 plus 4 times x sub I star divided by 3. Okay, so the hydrostatic force on that rectangle, I'll refer to that as F sub I, for the hydrostatic force on that rectangle. Well, it's the area of the rectangle multiplied by the depth. So the area of the rectangle is 10 plus 4 times x sub I star over 3 times delta x, and the depth is x sub I star. And then we multiply that by rho times g also for the entire hydrostatic force. Okay, so if we make this look a little bit nicer, F sub I is rho times g we'll distribute multiplication by x of I star, so we get 10 times x of I star plus 4/3 times x of I star squared times delta x. Okay, so if we get one of those for each of the n rectangles, and then take the limit of the Riemann sum, the hydrostatic force is going to be the definite integral from x equals 0 to 15. Since the lengths are measured in feet, rho times g is 62.5 pounds per cubic foot. And then we multiply that by 10x plus 4/3 x squared dx. Okay, this is a fairly simple integral to evaluate. And after evaluating it, that will give you the number of pounds for the hydrostatic force on one side of that trapezoid. Okay, we're almost out of time. I suppose until time runs out, we could go ahead and evaluate part of this. An antiderivative of 10x is 5x squared. An antiderivative of 4/3 x to the second is 4/9 times x to the third. Evaluate that from 0 to 15. Okay, we're out of time now, so go ahead and sign in for attendance.